Hey, this is Mr. Beckstrom. Today we're going to be looking at a pretty extensive problem from section 5.9. This is building exponential models from data. And what we're going to do is we're first going to put this information in our calculator. And then what we're going to do is we're going to fit it to an exponential function. So pulling up the calculator, let me clear this out. And we're going to go into Stat Edit. And I'm going to go ahead and clear out my old data by going up and clear Enter. So for L1, I'm going to be putting in the time in hours. So I have 0, 2.5, 3.5, 4.5, and 6. And for the population, which I'm going to put in my L2, which I commonly use with my Y variables, 0.27, 0.52, 0.75, 1, and 1.42. All right, and now I'm going to create an exponential function in this calculator. I'm going to go to Stat, go to Calculate, and I'm going to go to the exponential reg. So for me, it's 0. I hit Enter. Now, mine asks me for which two lists I'm going to use. And then I also want to store mine in my Y1 equation. If it doesn't come up with this, if it just comes up with a blank area, what you're going to want to do is you're going to want to put in L1, so that's second L1, and then you hit comma, and then you're going to hit second L2, comma, and then you're going to hit vars, go to Y variables, put in the Y1 there, and then hit Enter. For this one here, I go down and I just want to set vars, Y variables, Enter, and Y1. And this will store my function in Y1 that I can use later. Calculate, and this is what it looks like. So if I were to round this to 4 decimal places, remember this is A times B to the X. So A would be 0.2693 times 1.3263 raised to the X power. And let me write that out for you over here. So get my calculator on the other screen. So it will look like this. 0.269393 times B, which was 1.3263, 1.3263 raised to the X. So this would be my exponential function that would best fit this data right here. All right. Okay, the next thing I want to do is I want to express this function in the part A, which is here, in the form of, this is the decay function there. So the n of t is equal to n sub t, e to the kt. And in this case, it looks very similar to this right here. And notice what I can do is I can rewrite this, and I'll show you why in a second. E to the k. And then I can actually raise this to, okay, and if you recall, if you raise a power to a power, you can multiply those two powers together. So you can do the reverse of that as well. Since these two powers are multiplied together, you can write it in this form, which then looks much more like this form, which n naught, or n sub 0, is the 0.2693. the x will be our t, and then the 1.3263 is going to be our e to the k. So that way we can solve for k and then write it in this form. So I can write e to the k is equal to 1.3263. And to solve for k, I can take the natural log of both sides. So the natural log of e to the k. All right, and that is equal to the natural log of 1.3263. And if we remember from past videos, the natural log of e to something is just that something, because natural log and e are inverse functions of each other. They cancel out. So I'm going to get k is equal to, and natural log of that. So let's kind of figure that out to 4 decimal places. So get out of there, and we'll do natural log of 1.3263, and we get 0.2824. So 0.2824. And now I can go ahead and write this in that form there. So n of t is equal to, remember it is our a, so the 0.2693, and that is multiplied by, I'll do a multiplication something like this time, e to the kt. This is our k, and then we could just write t, kt. So 0.2824 t. And that is our answer for this question right there. Okay, next I want to graph the data with the exponential function found in part A or part B on the scatter diagram. Alright, so let's go back to the calculator here. Now what I'm going to do is I'm going to go to y equals. I already got that equation in when I saved it over. Now I want to make sure my stat plot is on using L1 and L2. I'll keep everything else the same there. And then I'm going to go to zoom stat. And that'll zoom around my stats. And it puts my equation right in there, and you can see that that line almost perfectly goes through that dots. It is the exponential function of best fit, meaning that there's no exponential functions that we can find that will fit those points or be closer to those points overall than these ones. And that's a least squares property that if you end up taking statistics, you will talk about possibly in there. All right, so that is that one. Okay, the next problem says use the exponential function from part A or B to predict the population at x equals 7 hours. And what they're saying is we can go to this one right here because this uses our x. So after 7 hours, what is this function going to be? Well, luckily we saved that in our y1, so this is a pretty easy one. So what we're going to do is we're just going to go back to our calculator, get out there, and we're going to do variables. Go to y variables. So that means we're going to pull up our y1 function, which was that exponential function of best fit. We're going to evaluate it at 7. So that means the population after 7 hours should be about 1.94. Let's go ahead and round up to 2 decimal places. 1.944. All right, so the last one that we wanted to look at here, and let me just go ahead and put the answer from the last one. So So n of t for this one when we evaluated n of 7. So n of 7 is approximately, what do we say, 1.94? 1.94. And then the last one I want to take a look at is it says use the exponential function from either part to predict the population when the population will reach 1.95. So remember, put that back here. The n of t, that's going to be the current population, which they're saying is equal to 1.95. So now I'm going to replace that with the 1.95. So that's going to be equal to, and we can use this one over here. So 0.2693 times 1.3263 raised to the x. So now we're solving for the x here. We're going to see how many hours it's going to take until we get a population of 1.95. And that's just from this kind of equation right there, or you can actually use that one right there, either way. And if you look here at our chart, it looks like it's going to be some amount of hours over 6, right? Because the population is growing, and 1.95 is larger than all of these. So I'm expecting a time that's going to be larger than 6. Since it's an exponential growth, maybe 7, somewhere around there. But let's check this one out. So first I'm going to divide each side by the 0.2693. So I'm going to get 1.95 divided by 0.2693 is equal to 1.32363 raised to the x. And remember, when we have a variable in the exponential place, we often want to apply either the log or the natural log to both sides to get it out of there. In this case, I'm going to apply the natural log to both sides. So I'm just going to write right here, natural log of this. All right, and let me give myself a little bit more space there. So I'm going to apply the natural log of this. Apply the natural log of both sides. That allows me to take the x in the exponential position and put it out in front of the natural log. So the natural log of 1.95 all over 0.2693 is going to be equal to, I'm going to move that out front, x times the natural log of, and I can only do that with logarithmic functions, 323,263. Alright. And finally, I am going to divide both sides by the natural log of 1.3263, and x is equal to, I'm going to do this part in my calculator and I'll round out to 2 decimal places, trying to stay consistent with my math lab here. So this is going to end up being the natural log of 1.95 divided by 0.2693, and this whole natural log is going to be divided by this one because we're dividing both sides by this, divided by the natural log of 1.3263, and I get 7.01. I should go ahead and make these approximations because we're rounding. So x is approximately 7.01 hours. And then I'm going to look back to see if it makes sense. Does it make sense? Yeah, because these are both, the population is higher than 1.42 and the hours are higher than 6. All right, that's a long one, but that's it. If you have any questions, let me know. I hope you have a great rest of your week. Thanks.